Okay, welcome back. Let's talk about attraction between molecules. So, why do I care about these dipoles and things? Well, the strength of the attractions between two molecules, whether they're ionic or covalent, will determine some of their physical properties. And so it is important. Molecules can be attracted to each other by various types of forces. These in between molecules, intermolecular attractions, are weaker than either an ionic or covalent bond. However, the number of those atoms or molecules doing that interaction is huge, and so it becomes very important. But among other things, those attractions are responsible for determining whether a molecular compound is a gas, liquid, or solid at a given temperature. So why is water a liquid at room temperature is dependent on those intermolecular forces. The two weakest attractions between molecules are collectively called the van der Waals forces. And this is named after Johannes van der Waal. You don't have to know his name. You do have to know van der Waal forces. And they consist of dipole interactions and dispersion forces. Dipole interactions occur when polar molecules are attracted to one another. This electrical attraction occurs between oppositely charged regions of a polar molecule. Dipole interactions are similar to, but weaker than, ionic bonds. A slightly negative region of a polar molecule is weakly attracted to the slightly positive region of another molecule. Dipole interactions are similar to, but much weaker than, ionic bonds. I think you should know these are weak. They're not bonds, but they are significant because of the numbers of attractions. Dispersion forces are the weakest of all intermolecular forces, and these are caused by the motions of the electrons around the molecule at any given time. These are fleeting. They do not last, but they are short-term, over-the-surface attractions between two molecules of any type. And I want this to be your next Easter egg. Every molecule has dispersion forces. You'll hear me call it London dispersion forces for the person who named it. So, London dispersion forces, or you can say LDFs. So it happens when these molecules are momentarily more on one side of a molecule than another, causing the neighboring molecule to reflect that change and have their electrons pushed around to correspond to an area of attraction. So if it's on the left side, we develop a negative charge. On the next molecule, the right side would become the opposite charge. The strength of dispersion forces generally increases as the number of electrons in a molecule increases. And that's because those electron clouds, A, get bigger, and they're more easily pushed around because they get further from the nucleus. So fluorine and chlorine have relatively few electrons, and these are gases at room temperature and pressure. They have especially weak dispersion forces. Bromine molecules, however, are starting to get fairly significantly large, and now it becomes a liquid at room temperature and pressure. Iodine is still larger, and it becomes a solid at room temperature. And so just the van der Waals forces are in play when we're talking about atoms that are bonded to themselves in a molecule. Hydrogen bonds are the next type of interaction. We have to have an oxygen, a nitrogen, or a fluorine with a hydrogen attached. These are highly polar bonds. The oxygen will acquire a slightly negative charge because of its greater electronegativity, and the hydrogens in the water molecules acquire a slightly positive charge. And so the hydrogen is attracted to the oxygen in one molecule, and we can do that hundreds of thousands of millions of times all over that molecule, or that, like even one droplet of water. This relatively strong attraction, which is also found in hydrogen containing molecules other than water, is called hydrogen bonding. We see this in our proteins, our DNA, and RNA, and all sorts of things. These are attractive forces. When a hydrogen is attracted to, or bonded to a highly electronegative atom, and it will be the same in a nearby molecule, and so now those hydrogen bonds get a very extensive network of bonding. Hydrogen bond has about 5% the strength of an average covalent bond, so it would only take 100 of these to make it as strong as a covalent bond. Hydrogen bonds are the strongest of the intermolecular forces. They are extremely important in determining the properties of water and biological molecules. Put a star by that. Number 2. Why are hydrogen bonds important? They are the strongest of the intermolecular forces, and they are extremely important in determining the properties of water and the biological molecules such as proteins and RNA and DNA. Intermolecular attractions and properties. What are the properties of covalent bonds so diverse? At room temperature, some can be liquids, gases, or solids, and it's because of those intermolecular forces that cause it to be that. Physical properties of a compound depend on the type of bonding it displays, in particular whether it is ionic or covalent. Diversity of properties among covalent compounds is mainly because of the widely varying intermolecular attractions. Melting and boiling points of most compounds are composed of molecules are low compared to those of ionic compounds, so covalent compounds melt very easily. Ionic solids take a lot more energy. Most solids formed by molecules. Only weak attractions between the molecules need to be broken. A few solids that consist of molecules do not melt until higher temperatures reached of 1000 Celsius or higher. Most of these are very stable substances called network solids or network crystals. These are solids in which all the atoms are covalent bonded to each other. The melting of a network solid will require the breaking of a large number of covalent bonds through the solid. An example of this is diamond or like lead, carbon lead. Here's a network solid of diamond. We can see that one carbon atom is attached to 4 other carbon atoms, and that makes it a network solid, and it gives it a melting point. It actually doesn't melt, it just vaporizes into carbon gas at 3,500 degrees Celsius. I'm not going to stop and read this to you, but this is something I will test on, so you'll want to have this in your notes if you don't already. So, we're almost done. Why do network solids take so much more heat to melt than covalent compounds? That's because the solid requires breaking a larger number of covalent bonds throughout the solid, and melting most covalent compounds only requires breaking the weak attractions between molecules. Key concepts. When different atoms bond, the more electronegative atom attracts the electrons more strongly and acquires a slightly negative charge. Intermolecular attractions are weaker than either an ionic or a covalent bond. Diversity of physical properties among covalent molecules is mainly because of widely varying intermolecular attractions. So your glossary: nonpolar covalent, polar covalent bond, polar molecule, dipole. You should be able to draw all dipoles. Van der Waals forces, dipole interactions, dispersion forces, hydrogen bonds, network solid. Whew, a lot of words. Okay, guys, that's it for today. I will see you in class.